Okay, let's get started. Good afternoon, everyone. Welcome to the HAO colloquium. My name is Dong Lin. Today, we are very glad to have Dr. Yin Zhou from the Applied Physics Laboratory, Johns Hopkins University. So first, let me introduce our speaker, Dr. Zhou, briefly. So Yin Zhou is a senior staff scientist in APL of Johns Hopkins University. Her research interests mainly focus on the Earth's magnetosphere, ionosphere, and upper atmosphere, and their dependence on the upstream solar wind. She has been actively studying plasma convection, auroral dynamics, and thermosphere circulation. She obtained her PhD degree from UCLA in 2015, and she was a postdoc at Boston University during 2017 to 2019, and an assistant professor in University of Alabama in Huntsville during 2019 to 2023. And today, Dr. Zhou will talk about upper thermospheric winds in the Dayside and the Nightside auroral zone. So please take it away, Steve.
Sure. Can you hear me okay?
Yes.
Great. Thank you so much for having me here. And today I would like to share my research on upper thermospheric winds. Some of the results are ongoing study. Any comments, suggestions are welcome. The title today is Upper Thermospheric Winds in the Dayside and the Nightside auroral zone. So we already know that winds are strongly affected by auroral forcing. So the figure here shows the upper thermospheric wind vectors overlaying onto aurora images. And the fact that these vectors are very well organized by the auroral oval suggests that they are driven by the two-cell convection on a planetary scale. But the question I have is, are winds throughout the auroral oval driven in a similar manner? Or more specifically, are winds driven in a similar way in the Dayside and Nightside auroral oval? So why do we question that? Well, in fact, simulation already suggests that wind forcing is quite different on the Dayside and Nightside. So here show the distribution of wind forces as a function of either pressure level or height. And the wind forces include the Coriolis force, ion drag, advection, pressure gradient, and the viscosity. So the forces are decomposed to zonal and a meridional direction, and left is midnight, right is noon. So at midnight, the winds, especially in the upper thermosphere, have a very large net westward acceleration. And this acceleration is mainly due to the Coriolis force here and the ion drag at higher altitude. On the other hand, at noon, there's little net acceleration. And this is due to the balance between this ion drag here and also the Coriolis force and advection here. So in the meridional direction, even though both midnight and the noon winds have little net acceleration, the specific force balance is very different. So the balance at midnight is between this pressure gradient and ion drag and the Coriolis force. But at noon, it is due to the Coriolis force being balanced by the pressure gradient and also the ion, this is advection. So there's really no need to memorize these forces because it's going to change with geomagnetic condition. But this event just shows us how different the wind forcing is at noon and midnight. This difference in forcing shouldn't be surprising because even from textbook knowledge, we know that the energy input into the thermosphere is different on the Dayside and Nightside. So let's start with plasma convection. Convection is important because it affects the ion drag. It also modifies or modulates the Joule heating rate. So here just show the Superdarn-derived climatological patterns of ionospheric convection. Left is negative By, right is positive By. So on the Dayside, you can see the convection is strongly dependent on IMF By, directed, this is eastward, for negative By and westward for positive By, and the reverse is true for southern hemisphere. The Nightside convection still shows some dependence on IMF, but to a much lesser extent or degree. On the other hand, the Nightside convection is strongly dependent on disturbances in the geomagnetic tail, for example, substorms. And here show the Superdarn-derived superposed epoch convection pattern for substorms. And yeah, so this is growth phase, onset, expansion, and recovery phase. So for Nightside convection, let's just focus on this red box. During the growth phase, the convection is fairly strong, and this is mostly indicated by the cross-polar cap potential drop here. At onset, the convection, to a large extent, looks similar to the growth phase, even though a closer inspection may suggest more structured flow embedded within. So during the expansion phase, the convection is drastically reduced. So initially it is this orange, yellow, green, but now it is dark blue. And this reduction of convection gradually recovers during the recovery phase. On the other hand, if we look at Dayside, there's no such systematic evolution associated with substorms. Okay, besides convection, particle precipitation is also important because it affects ionospheric conductivity and therefore the ion-neutral collision rate and the Joule heating rate. And here I'm just showing the DMSP-derived aurora precipitation model. I use diffuse precipitation as an example. The left column is energy flux, and the right column is particle or number flux. So if we look at Dayside, which is this top portion of the auroral oval, the energy flux is much lower than a Nightside, but the number flux is much higher. And this is true for both low solar wind driving condition and also high solar wind driving condition. So that means precipitation on a Dayside is soft or of low energy. So this kind of precipitation is important for conductivity in the F region ionosphere. For the Nightside, the energy flux is high. The number flux is either low or modest during high solar wind driving condition. But nevertheless, the precipitation is of high energy, and as such, high energy precipitation is important for E region conductivity. Last but not least, we have the Poynting flux, and the left shows this swarm-derived alphinic Poynting flux. So they filter the Poynting flux to spatial scale to 10 to 100 kilometer. And yeah, in both hemispheres, you can see a strong peak on the Dayside. The Nightside, not so much. The right-hand side shows the DMSP-derived Poynting flux. I believe this flux has not been filtered in scale, so it can include the DC component. But nevertheless, during quiet time, which is this top row, there is a strong peak on the Dayside. And during active time, the Dayside is still strong, but we have more flux going to the dawn and the dusk auroral oval. So that means, plasma convection, precipitation, Poynting flux are all different on the Dayside and Nightside. So let's just look at a few observations about wind in these two regions to see whether the two are similar or different. Overall, measurements of wind on the Dayside are limited, but here shows wind measured by high wind. So this is a balloon-based FPI by Qian Wu at HAO, and yeah, so it's basically an FPI, but equipped onto a balloon. And as the balloon drifts and Earth rotates, the measurement made during a day can be displayed in this polar plot. The blue vectors are wind measurements, and this high wind measure winds both polarward and equatorward of the flight track. So that's why you see two rings of wind vectors. The red is ion drift. The green is the prediction by simulation. And one striking feature here is that there is persistent equatorward directed wind, even when the simulation predicts that the wind should flow polarward. So that indicates that there is an additional or equatorward force involved that turns the polarward wind equatorward in order to have the simulation and observation consistent. And one candidate for this, additional equatorward wind force is found to be related to the additional cusp energy and associated with an associated pressure gradient. So the figure on the right shows the difference in wind vectors when you simulate the cusp with and without additional energy. So this energy basically is Poynting flux and a soft electron precipitation. So this energy heats the cusp region, modify the pressure distribution, and this change turns wind equatorward of cusp, equatorward, and winds polarward of cusp, even more polarward. So this equatorward force is interpreted to be responsible to produce such equatorward winds. Here's another study. This is a statistical wind distribution based on CHAMP horizontal wind vectors. And it shows it shows more, but here I'm only show 3 patterns that's under different IMF-BY. We overall see the day-night flow in the polar cap and a return flow on the 2 sides of the auroral oval. But for dayside wind, let's focus on the red box, which is about 65 to 80 degrees. Even though we do not clearly see the equatorial wind like in the previous slide, we see something unexpected, that is wind flow westward regardless of the direction of IMF-BY. This is very different from plasma convection because for negative IMF-BY, plasma should flow eastward. So the zonal components are going in the opposite direction between wind and plasma. With that said, the magnitude of the wind changes with IMF. So the wind vectors are longer for IMF-BY, for positive BY, and are shorter for negative BY. For the Nightside wind, I'm just going to focus on substorm time because, as we indicated earlier, Nightside convection is strongly affected by substorm. So for substorm-related winds, one controversy is whether winds respond to substorm. And here is a slide showing there's little or no response. So what is shown here is superposed CHAMP observation showing change of wind speed following onsets. So the y-axis is velocity relative to the pre-substorm value, and this is the y-axis. X-axis is the latitude. So as the CHAMP satellite orbits, it covers a wide latitude range. The red curve is the first orbit after substorm onset, and blue is second, green is third orbit afterwards. So you can see that within the aurora zone, the delta V relative to pre-substorm is very small, like 20 meters per second. So this is regarded as a weak effect. But there are also studies showing quite a significant effect. So here is a case study of FPI. From top to bottom, we have aurora observation. This is zonal wind, the acceleration rate of the zonal wind, meridional wind, and acceleration rate of the meridional wind. Different phases of substorm are represented by the color bars at the top. So following the onset, you can see the wind show eastward or turn eastward and southward. And this amplitude is quite significant, like 200 meters per second. That's 10 times larger than the previous slide. And if you look at the acceleration rate, there is eastward acceleration in a late growth phase, expansion and recovery phase, and southward acceleration in a late growth phase. So yeah, there is significant subswarm effect in this event. So here's our motivation and the data sets. As indicated earlier, we are interested in understanding whether winds are driven in a similar way in a Dayside and Nightside auroral oval by plasma convection. We use what is called scanning Doppler imager. It works very similar to FPI, but the difference is that SDI collects sky emissions from a wide field of view. As traditional FPI, they have a narrow field of view, and it has to rotate to a different direction in order to obtain a wind field. So the advantage of SDI is to have this simultaneous or nearly simultaneous wind measurements over a wide area, so we can separate spatial temporal effect. The Doppler shift gives the line of sight wind speed. Doppler broadening gives the temperature. We mainly use line of sight speed, although the speed has already been fitted to derive the wind vectors. There are several SDIs distributed across the globe. We mostly use South Pole for Dayside wind measurements, and the Poker Flat, Toolik, and Kaktovik for Nightside winds. Okay, so I'm going to start with Dayside wind. Our goal here is just to understand wind field under IMF with different signs of BY, because IMF BY is a critical controller of plasma convection on the Dayside. And our approach is just to survey steady IMF so that changes of wind mainly reflect spatial rather than temporal variation. In this way, we construct a 2D wind field. And in the following slides, I'm just going to show 2 case studies and a binned multi-event analysis. We would like to have statistics analysis, but the database is too small for statistics. What's shown on the right is the 2 SDI located in the southern hemisphere. So this is South Pole. There's another one at McMurdo. I only use South Pole for this study. 2 reasons. First, South Pole, the location is closer to the nominal location of the cusp. So South Pole is like 75-degree magnetic latitude. McMurdo, I think, is higher at higher latitude. And the second reason, frankly speaking, the data files on the SDI website contain arrows for both stations. And so far, I've figured out how to correct the South Pole, but I haven't got my hands on to the McMurdo yet. Okay, so here is the first case study. This is a negative IMF event. Negative IMF BY event. This panel on the left shows IMF BY component. It is negative for almost 7 hours, so covering the few hours when South Pole was on the day side. The middle panel on the right is the super darn fitted velocity vectors. And you can see the rounder cell at dusk and a crescent cell at dawn. So this is southern hemisphere, which is why it is almost a mirror image of the northern hemisphere convection cell. And the South Pole SDI basically drifts around this dashed circle here about 75-degree. And the selected snapshots are just shown here to represent the wind field. So let's first focus on the zonal component and see how the zonal component varies from this morning side to the afternoon side. Within the auroral oval, which is this aurora emission region, the zonal wind is first eastward and then becomes fairly small and then turn westward and westward. So this change from eastward to westward is consistent with, at least qualitatively, with what we expect from the plasma convection. Now, polarward of the auroral oval, the wind is first weakly eastward and then westward, westward, and westward. again, consistent with plasma convection. Now moving on to the meridional winds. So within the auroral oval, first, there's not much meridional wind, but then there's significant polarward wind, same here, same here. So this is slightly different from convection because you can see these polarward winds seems to come from a lower latitude and they flow across the auroral oval. Plasma convection, on the other hand, generally flows zonally within the auroral oval. Now into the polar cap, there's little polarward wind, little polar wind. Again, we have winds there, but it's mostly, zonal, not much polarward wind. This is, again, slightly different from convection because we often expect, within the polar cap, plasma convection have an anti-sunward component. But yeah, that's anti-sunward component is not clearly seen, or at least seem to be deflected in the wind pattern. So the similar wind characteristics can be seen from this time series plot. This is the same event. From top to bottom, we have aurora, zonal plasma convection, zonal wind, zonal, this is meridional plasma convection, and this is meridional wind. And again, this is about 7 hour long, and midnight, is slightly before 16 UT. So comparing the zonal plasma convection, zonal wind, we see similar transition from eastward to westward wind. So this is eastward to westward convection, same in the polar cap and aurora zone. But the main difference is in the meridional direction. Here you can see the meridional direction, at least for the few hours centered around noon, there's a strong polarward wind that seems to move across the equatorial boundary of the auroral oval. The plasma convection, on the other hand, there's not too much. There's some polarward plasma convection, but not a lot. The strongest plasma convection is polarward of the auroral oval. But for winds, the polarward component is really weak. We can check this significance about this, meridional component in a different perspective. That's where we take the ratio between the zonal and the meridional component. So that essentially tells us the angle from the northward direction. For plasma convection here, you see a region of nearly zonal, this is a meridional convection, and that's probably where the convection throat is. And eastward of this convection throat, we have this broad zonal region, polarward and within the auroral oval. But this pattern is very different for winds. So even within the convection throat, the winds are more zonal. But like eastward of the convection throat, within the auroral oval, we have this polarward wind. But polarward of the auroral oval, we have the zonal wind. So it is more polarward within the oval and more zonal polarward of the auroral oval. Yeah, this is a little complicated, but yeah, I will show a cartoon at the very end. So the take-home message here is that for negative Vy, the zonal components of the wind are qualitatively consistent with plasma, but the meridional component is not. So now let's look at a positive By condition. So here the IMF is mostly positive, except for a few excursions. And this positive IMF Vy lasts even longer than 7 hours on the day side. And the figure, the middle panel on the right, shows a plasma convection, round cell on at dawn, and the crescent cell at dusk. Now, looking at the winds. So again, starting from the zonal components, within the oval, the zonal winds are eastward, again eastward, still eastward, and still eastward. So there might be some westward wind at the edge of the field of view, but speaking of most part of the field of view, it is eastward. So this is quite different because if you look at plasma, it is transitioning from eastward to westward. But here, winds just flow eastward across the day side. Now, looking at polarward of the auroral oval, the zonal component is first weak, but then westward, westward, still westward. And this is, again, very different from plasma because plasma is showing eastward convection, polarward of the auroral oval, almost, essentially just across the entire day side. So that means the zonal wind is flowing against the plasma convection. In terms of meridional wind, we have polarward winds, little polarward winds, but again, polarward winds. So that's similar to the previous event where we have winds flowing across the auroral oval. And the polarward of the auroral oval, we always see those polarward winds. The same thing here using time series plot. And by comparing this zonal component of plasma convection and the zonal component of wind, we can see the drastic difference. Within the auroral oval, it's almost always blue color. It turns weakly red only at the very end of the interval. But here it's blue and then transition to red starting maybe 1 hour earlier than the wind. The drastic difference happens polarward of the auroral oval. Here you can see purely blue until here. The wind have some westward convection. Sorry, this is plasma. The plasma turned westward slightly over this interval. But for wind, it is first weak, but then strongly westward and all the way till the end. So again, this difference in red and blue suggests that the wind and the plasma are flowing against each other. Speaking of the meridional wind, especially around noon and post-noon, we see the strong wind within the auroral oval. There's also strong wind polarward of the oval, so that's consistent with plasma convection. But the strong wind within the oval is not. In the pre-noon sector, the polarward wind is weak. So we collect event like this and just conduct the superposed analysis. The left column is for minus by, the right column is for positive by. So the top panel just show the number of events, not a lot, but a few up to 10 or something. The second panel is zonal wind, meridional wind. So for negative by, we see from the zonal wind, we see the transition from west to east. So that's similar to plasma. But the meridional wind is different. The main difference is that it is strong in the equatorial half of the field of view. So that's usually within the auroral oval, but it's weak, polarward half of the field of view. So that means winds are more polarward than plasma within the oval, but less polarward of the oval. So here is kind of like a summary where the zonal direction are similar, but winds are more polarward within the oval, but less polarward. Polarward of the oval. For positive by, on the other hand, you can see that similar to the case study, winds in the polarward half of field of view always direct westward. And equator within the auroral oval, it always direct eastward. And indeed become weaker, but there seems to be this preference like to east and west seems to be always there. And for the meridional component, we still see the strong wind moving across the auroral oval. And polarward of the auroral oval, the variation is more subtle, but it seems to be more like relatively polarward, not so polarward, and relatively polarward. So that is summarized here, where you can see that within the oval, wind first flow in a similar direction within the dawn cell, but it starts to flow against plasma once it goes to noon and also post-noon. With respect to polarward of the auroral oval, it seems to always flow against the plasma convection. So let's compare this pattern with the earlier study we mentioned, made by Champ. So this is negative IMF BY for southern hemisphere, positive BY for northern hemisphere, the same on the right. So by looking at the zonal components, we find a similarity where, especially for winds polarward of the oval, there is a preference to westward wind, regardless the sign of IMF BY. And also the magnitude varies with IMF. So it is stronger, when wind flow in the same direction of plasma, but weaker when wind flow against plasma. Things that cannot be tested or confirmed from this comparison is the effect of meridional winds. We cannot say clearly, whether there's this deflection of wind relative to plasma from Champ. And also, in both these two studies, we haven't seen the equatorward winds as seen by the high wind measurements. So we are really puzzled why wind can flow against plasma convection. Apparently, this needs forces other than ion drag. And in the end, we would like to have simulation informing us what's happening. But here I'm just going to have some hand-waving analysis based on, theoretical or just based on imagination. So first, the Coriolis force can be important because in the southern hemisphere, it can turn southward wind westward. So that may explain why in the polar cap, the winds are less polarward, but also showing a preference to the westward wind. The eastward wind, the Coriolis force may also turn the eastward wind southward. So that for the dawn cell wind, it may explain why winds within the oval can be more southward or polarward than the plasma convection. There might also be contribution from pressure gradient force, especially day-night temperature gradient. So that can drive wind flowing across the auroral oval. But what is unclear is the role of cusp heating, because in the introduction, we show that, when there's cusp heating, we have this localized spot of high temperature, and that's going to deflect winds equatorial cusp more equatorward, and winds polarward cusp more polarward. But unfortunately, we are not clear the role of that cusp heating here. Okay, so hopefully in the next 10 minutes, I can finish talking about Nightside winds. I've talked about this quite a few times, so if you have heard about it, feel free to stop here. But the goal here is just to understand wind field before and after the substorm onset to see, how efficient plasma convection is driven wind. And our approach is somewhat similar to the Dayside study, but because substorm is not steady, so during the few hours of SDI measurements as the station rotates, we cannot assume the measurements are spatial rather than temporal. So instead, we need wind measurement at various local time relative to onset in order to piece together the wind field. And for here, I'm also going to show 2 quick case studies and have a superposed epoch analysis. So this is the first case study. This is made, I think, around in the pre-midnight local time. So from top to bottom, we have AE index, Aurora from Themis All-Sky Imager. I'm only showing the zonal component here. This is zonal plasma convection by Pfizer and the zonal wind measurements. So the zonal winds are kind of like a perturbation from a baseline. We construct a climatological baseline based on geomagnetic quiet time. So this is a perturbation from that. And also you may notice that this is a very tall panel, and that's because we require simultaneous SDI measurements from 2 locations so that we have ideally the wind measurements across the entire auroral oval, so covering a wide latitude range. So following the onset, we can see the wind pattern change a lot. The previously westward directed winds within the oval turn eastward, and the previously weak wind now turn westward. And this magnitude change is about 100 up to 200 meter per second. This is an event happening in the post-midnight. Following the onset, you can see the plasma convection show enhancement, like become more blue. The wind measurements, the previously eastward wind now become westward. The previously westward wind now become eastward. Again, quite a drastic change. So we collect, these kind of wind perturbations, and we in the end up with 6 different. So the ones we just showed happen in the middle panel. So we have, oh, by the way, this is superposed. So 0 latitude is onset latitude, 0 time is onset time. The top row is zonal wind, and the bottom row is a meridional wind that I didn't show in case study. Yep, so I was saying that the previous 2 case study happened in the middle column, as we see here. This is the first event, westward wind turn eastward, weak wind turn westward. This is the second event where, the previously eastward wind turned westward, the previously westward wind turned eastward. What I didn't show was the meridional wind. So for all the 3 type of wind response at the bottom panel, you see southward acceleration. So this variety of wind response can be intimidating, but when we organize them according to the local time relative to the onset, we start to see a coherent picture. So this is kind of like a summary of the wind perturbation. So here is before the onset or the late growth phase. We are looking at a polar plot focusing on the Nightside. The magenta curve is onset latitude. So what we see is that there is an enhanced sunward circulation, so going towards Dayside, mostly above and also around the aurora onset latitude. For those on the post-midnight, these sunward circulation also have a southward component, so that's probably due to the deflection of Coriolis effect. After the onset, the wind perturbation can be categorized into 2 types. One is outside this blue shading region. For these vectors, they again show enhanced sunward circulation. This is similar to the growth phase, but different in terms it spans a broader latitude as well as longitude. But within this shaded region, the zonal wind is greatly suppressed and basically just acting in the opposite direction of pre-existing wind. There's also southward winds at midnight and also post-midnight. So why do we have this suppression region, like this blue shading region? Well, if we compare with plasma convection, a similar region has also been identified. So this is substorm-driven plasma convection. The black shading region is where the zonal plasma convection is suppressed or become really structured. But outside the shading region, the plasma shows enhanced convection towards the Dayside auroral oval. So this great similarity between this plasma convection and also the wind distribution suggests that the wind can be mostly or at least largely explained by the ion drag. The southward wind, on the other hand, they are not here, but they are probably due to, for example, Joule heating, because this blue shading region is where aurora precipitation is very intense. And on a post-midnight, it's probably due to the Coriolis effect. So here is just my summary. So what we find is that on the Dayside, winds generally flow westward, regardless of the sign of BY. So that means for positive BY, winds are going to flow in the opposite direction of plasma convection. But even for negative BY, where the zonal components agree, the meridional components do not agree. winds are more polarward than plasma within the oval, or less polarward than plasma polarward of oval. So that means either case, whether positive or negative By, winds are going to form a significant angle from the plasma convection. And that means that winds are significantly affected by forces other than ion drag. The nature of these forces warrant future study, but a few candidates: Coriolis force, pressure gradient force. On the night side, on the other hand, winds resemble substorm-related changes in plasma convection. The original winds can have a southward component, but yeah, to a large extent, wind can be explained by ion drag, with the small difference likely due to Coriolis effect and the Joule heating. Yeah, so to answer the question we start at the beginning, winds on the day side and night side are driven quite differently. Ion drag seem to be more important on the night side than day side. I'm happy to take questions here.
Okay, thank you, Ian. Let's give a round of applause. So question time. Chat, please.
Yeah, the night side solar wind tend to be, it's hard to pin down, and sometimes they go eastward, sometimes they go westward. It also changes from sometime near dusk, which tend to be eastward, and once you go over to dawn, that's more westward. So in the midnight, you have this transition. Is that correct? Between more eastward zonal wind to westward zonal wind.
Yes, like the, I guess around the Haran, right? Is that what you're saying?
Yeah. I think that is where the transition happens. It depends very much on your IMF conditions. It looks like, is that correct? Am I taking this correctly?
Yeah, I think it's affected by IMF, but also by main-to-tail processes.
Okay, I see.
Hi, a question on the you said the day side, oftentimes the wind and the drift are against each other. So does that produce enhanced like a Joule heating there? And if so, if you see any heat anomaly or temperature bulge or something in that region?
Right. So in this simulation, if we include additional cosp energy, then we should have something like a temperature peak, or even the thermosphere density anomaly. I think that's what it's called here. And if that's the case, the pressure gradient should push the wind equatorward here and a polarward here. Whether that can explain the westward preference is something I'm not clear, because here it doesn't seem to show a westward preference, especially polarward of the Auroral oval is actually flowing eastward. Yeah, so my guess is I think the cosp energy is important and it should be there, but what role it plays to this westward preferred wind, I don't know for now.
I see. But if it does form some kind of temperature maximum there, that may also produce a pressure gradient. Will that tend to slow down the wind?
I guess if we look at here, these are the perturbation associated with the pressure gradient, right? So it will slow down the wind on the dawn side, maybe not so much on the dusk side. So I guess it depends on the relative location to the cusp here. Yeah, but whether that gives the westward preference wind, I'm not clear, because it doesn't show this westward preference only based on this simulation.
Yeah, I also have a question about the coordinate system. Since you are referring to the plasma convection, I assume you are mainly using the magnetic coordinate.
Yeah, like ACGM.
So is that we'll talk about the wind, like a zonal meridian direction. Is that also based on the you say
Yes.
ACGM, right?
Yep. Yep.
Okay, but in that case, it's not totally aligned with. Actually, it has can have a large deviation from the rotation axis, and how does that affect the Coriolis force effect?
That's a good point. I didn't think about the. I guess yeah. Now I think my head waving analysis of Coriolis force is two cores. Yeah, especially in the southern hemisphere, the south pole. I mean, the geographic and geomagnetic pole are quite offset. So now my analysis was mostly in the magnetic coordinates, but strictly speaking, I probably should analyze the Coriolis force in the geographic coordinates. And yeah, I think that's something I need to look into on top of my head. I don't know how that's going to change the direction of the deflection. Yeah.
Right. I would look forward to the further analysis I'm going to do. Actually, this wind response to the magnetospheric forcing is also something we're about to study with a image model. So we'll probably have a lot more to discuss in the future.
That would be great. Thank you.
So more questions.
Yeah, another question maybe, since you have time here. So South Pole is more of a poleward of a cusp, is that correct? Or it's right underneath?
I think it depends on the geomagnetic condition, right? During during active time, it can be poleward of the auroral. I mean
the cusp.
Yeah, the cusp. I think typically cusp varies from 70 to 80 degree magnetic latitude, and that's about the field of view range of the South Pole. So for the event we try to select, where at least the aurora emission stay well inside the auroral oval, well inside the field of view, so that we see the wind within the oval and also poleward of the oval.
You don't see much of like equatorial winds at South Pole during the wintertime on the dayside.
Right. I think that's a good point. I mean, it can be due to, our conditions are generally quiet, not quiet, but not too active. So that maybe the soft precipitation or the pointing flux to the cusp is not strong enough to turn wind southward.
Now, in some high wind observations, we do have a new high wind observations 2018. If you're interested, we can certainly give you those to work with. And they do see a little bit dip at noon. That the Mariana wind seemed to be sort of less. Have some kind of double hump features that seem to be affected by the cusp heating, but it doesn't seem to show in the wintertime. So in wintertime, you're probably less affected by the cusp heating than during the summertime. But unfortunately, summer is difficult to see. You don't have observation in the summer. So,
yeah, that seasonal dependence is, I guess, probably the day-night temperature gradient is also larger during the winter time, if because South Pole is in the dark. Maybe during summertime it's still under sunlit. So I guess that's probably another factor. So there's stronger heating and a less counter effect from the day-night temperature gradient. Yeah, it would be nice if we can have a broader season coverage, but The SDI, I think that's the limitation of SDI, only operate during winter
Yeah.
season.
It's hard to say, that in the daytime you have a higher ionosphere densities, and that probably drag, I don't know, they drag the neutrals because ion doesn't want to move that much, and during the nighttime you don't have much ionosphere as during the daytime. So the ions and both ions and neutrals are free to move around a little bit more, less constrained probably. So.
Yeah, I have a related question. So for this wind data, it's mostly from the SDI. What's the typical altitude again? You were referring to upper atmosphere.
Right. So this is a red line emission. It's in reality very broad, but here we just assume it comes from 250 kilometer.
And also,
Nice talk. Thank you much. Really nice talk.
Thank you.
I have one last question. So could you remind me what's the typical response time of wind pattern?
Oh, that's a very good question, because I think there's no consensus there's more study on the night side. So fast one can be like as short, like something a few to 10 minutes. Long ones, there have also been reports like a few hours. So my understanding or my guess is that the local, plasma density really plays a role. So if you have around auroras, what we find is that the response is really fast, likely due to the particle impact ionization associated with aurora. But far away from the aurora, let's say in a subaurora zone, it can take much longer.
But I think one thing good is that in the two cases you showed, they're actually very close to each other. So at least the seasonal effect is not a big one. Okay, other questions? Okay, Gang, please.
Yeah. Yeah, it's a really nice talk. I really enjoy it. So just follow on the question about the responding time. So like you said, well, the aurora zone response time will be much shorter and the subaurora will be much longer. But if I read correctly, that you're almost like close to the last slide, you see the different events across the aurora oval from a polar to equator of the onset time, but it's like it's spontaneous response rather than this, anticipate the latitude dependence. Maybe I'm not reading right.
I think you're right. So sorry, got too fast. So I would regard most of these events happen within the auroral oval, because once you have substorm, it like the oval, the ionization enhances. I guess there's polar expansion, but there's also gradual equator expansion. So this entire area actually is within the auroral oval.
Okay.
So that's why the response time.
About this one, that's right. So so this one, you said that the 0 is the onset region, right? So for all these events, the aurora oval covered the entire regions of 10 degrees or so? Is
more
that
or less, yeah. So here, well, this is about 10 degrees from the onset latitude. So I would say in this case, by averaging all events, looking at the large scale, the response time is probably 30 minutes. Like it starts to change immediately, but reach kind of like a somewhat quasi steady state after 30 minutes. So here it probably stabilized somewhat here, but so that's the time scale I would see here. Does that answer your question?
Yeah. That's right. Okay, I see. Yeah. Okay, I got it. Thank you.
No problem.
Okay, thank you, Gang. And more questions?
I have a question, or maybe it's more of a comment, Ying, for the effect of cusp heating. And the it depends on the altitude. It'd be nice to have wind measurements at, a variety of altitudes going up to 400, 500 kilometers.
Probably. Yeah.
But, and, it depends on whether that cusp heating has much of an effect, which you don't really see in the FPI-derived winds at 250, are assumed to be 250. But if energy is deposited in the ionosphere and then shows up in the thermosphere at higher altitudes, you probably wouldn't see it at the lower altitudes, because the thermosphere is getting so much denser as you go down. But it may be a reason. It's just a comment, an idea about why you may not be seeing the effect of cusp heating in the winds because of the altitude of the measurement.
So are you saying that the heating may happen at E region and we are able
No, I'm actually saying it happening at F region, above, maybe above where the, to the extent that the FPI derived winds are at 250 kilometers, if the heating is happening more at 350 or something like that.
so even higher.
Even higher. Yeah. I mean, that's what you get. You get higher altitude energy deposition when the source of the heating is delphinic as opposed to quasi-static or DC.
Yeah, that's also a good point.
Yeah, it's just I don't know how one gets at that. Looking at the altitude dependence of the wind, it's really a tough problem. But
yeah,
just an idea.
Yep, I think that's nice input. Thanks.
That's a lot of discussions. May I ask, are you coming to Boulder for the workshop, CGS workshop?
I think I probably join remotely.
Okay. Well, anyway, I think we still have a lot of chances to talk with colleagues here, and yeah, it's really nice talk. Let's thank Ian again.
Thank you so much.
Okay, thank you, everyone.